to thank Manas with his busy schedule to make it out to deliver a talk and share his thoughts. So I'll now request my student to introduce Manas.
Good afternoon, all of you. Now we are going to start our talk on the topic impact of high penetration of inverter-based generation on power system dynamics, control and protection by Professor Manas Kumar Jena. But before that, I am honored Kumar Jena. He received his PhD in Power System Engineering from Department of Electrical Engineering, IIT Delhi, and currently serving as an assistant professor in the Department of Electrical Engineering, IIT Palakkad. Before joining IIT Palakkad, he served as a subject matter expert at General Electric Power. He is recipient of the Indian National Academy of Engineers Innovative Student Projects Award 2018, Doctoral Level POSOCO Power System Award 2019, GE Impact Award 2019 for the development and delivery of Phasor Analytics software solution to ONS Brazil and Indian National Academy of Engineers Young Engineer Award 2021, and he is an associate editor of the IIT Generation Transmission and Distribution Journals. By this, I would like to call Professor Manas Kumar Jena to deliver your talk. Thank you, sir.
Okay, thank you, Professor Manoranjan and students. Okay, let me try and share my screen. Okay. So, Manoranjan, can you confirm?
Yes, it's visible.
And I hope my voice is clear and louder.
Yeah. You can please carry on.
Okay, let's see. Okay, so good afternoon, all of you. And for the next 1.5 hours or so, we are going to have discussion on this very important topic, that is impact of high penetration of inverter based resources, IBRs, that we generally use this term IBRs, on the power system monitoring, dynamics, control and protection. So basically you will see that this talk is divided into two parts actually. The impact of IBRs on dynamics control monitoring, one aspect, and protection, another aspect. So we'll first complete one part, I'll then can take questions on that, and then we'll touch upon the protection aspect, how the IBRs are going to impact the legacy power system protection schemes. These are the outlines of this presentation, introduction, challenges in the presence of renewable energy resources, and here I am only looking at IBRs, possible solutions and closing remarks. Our grid is evolving, all of us agree. So traditionally we were having conventional resources where we are heavily dependent on fossil fuel based plants, thermal plants, nuclear plants, and also conventional resources such as hydro. And how it is changing, how the landscape is changing, how the grid is evolving. So this is what is happening. You can see the transition. So in future we are looking at more and more of inverter based resources getting integrated into the grid. And you may be wondering why I have done like this, capital to small, because all of us know that if we are using conventional resources, that means we are essentially utilizing the synchronous machine based generations. If we are using synchronous machine based generations, one thing which comes with this type of generation free of cost is the inertia, capital H. And now with this transition, that's how the inertia by default that we are getting is reducing. So high system inertia to low system inertia is something which we are looking towards in the future. So reduction in system inertia, we may expect greater and regional variability in frequency. The grid management, if we look at, it has to be now proactive instead of reactive. We will understand the importance of each of these terms slowly in this lecture. So what we committed as far as India as a country is concerned, what we committed. So at COP21, as part of its nationally determined contributions, India had committed to achieve 40% of its installed capacity from non-fossil fuel based generations by 2030. Also, we have our Honorable Prime Minister has announced the commitment of achieving 500 gigawatt of installed generation capacity from non-fossil fuel sources by 2030. You can see we are actually committed to have more and more non-fossil energy sources. That means essentially we are looking at a grid with more and more inverter-based resources, whether it is solar or wind. More and more IBRs are going to get integrated into the system. So what are the challenges? So the challenges in stable grid operations, whether the grid will remain secure following contingencies, how the legacy protection schemes are going to operate. These are the things which need a lot of discussion, research, so that our grid will be prepared for the future mix of generations. Few statistics, renewable energy footprint in our country. If you look at this map is very important. I'll come back to this map again when I'll be discussing about inertia distribution. If you look at this plan, this particular map, we can see that southern side, western side, northern side, this is where we have a large footprint of renewable energy. Green color you can see. Eastern side, you are from Odisha, I am also from Odisha, we can see we have mostly the traditional generations. But this side we can see that we have very nice footprint for the renewable energy sources. And on the right side, if we look at what are those, we can see the solars, orange color, wind, and the hybrid plants also. So essentially western side, northern side, southern side, we are looking at very nice potential as far as RE is concerned. Few more statistics. This is the present scenario, March 2023, what the statistics we had as far as hydro is concerned, solar is concerned, and wind is concerned. And if we want to meet the target that our Honorable Prime Minister had, so then how much of addition we need to do? These three are important. You can see we need to add more and more hydro as well as solar and wind. More than 300% you can see as far as solar PV is concerned. On the right side, if we look at the demand, 2023 to 40 gigawatt, and we are expecting somewhere around 366, the maximum demand met. So that is what we are expecting for 2030. So grid is evolving very nicely, very aggressively, we can say, and so as an operator, as a system engineers, we need to prepare the grid for these challenges or the scenarios that we are going to face in the future, right? These numbers at least will give us some statistics or some motivation what we are going to face in the future, right? Okay, so with all the statistics and the numbers that we have in our mind, we should ask ourselves the question, let us have more and more inverter based resources such as solar and wind, then what are the issues? Why should we worry? This is where for the next 5-10 slides we will touch upon those aspects. The first aspect is inertia. What is inertia? It is, in the layman perspective, it is nothing but resistance to change. So in the power system perspective, what is that resistance to change in what? So this is nothing but we look at change in frequency after any contingency. So that means If in our grid we have very nice inertia with us, and following any contingency, other it is a large generation loss or a large load loss, if we have very nice inertia with us, okay, so that means that will help to arrest the frequency deviation. And luckily we have the synchronous inertia, which is essentially referring to the kinetic energy stored in the rotating masses of the conventional machines, which takes care of this inertial response, isn't it? In our control theory we have studied power system control theory. After the contingency, the first thing which comes into the picture is the inertial response. From where it comes, this is what helps us, right? And it is there by default, inherently it is part of the machine, right, which helps in arresting the frequency deviation, right. So a system with large amount of inertia reduces the rate at which the frequency change following the contingency, this so called rock off, rate of change of frequency, right. And typically we express the inertia in seconds, so typically varies from 2 to 10 seconds or so. So what is the physical interpretation of it? That means it is the time for which, time in second for which the machine can supply its rated power only from its stored kinetic energy. This is what we refer to as the inertial response following a contingency, right. So this is what is the role of inertia in the grid. To further understand this very nicely in an intuitive way, if you can look at this particular figure here at the right side, we have, let us say, water filled inside it, you have a tap here, water coming out, you have also incoming water going into the beaker, right. So here if you look at, so you think of this as the generation, what the water going in is nothing but the generation, analogous to generation. The water coming out is nothing but the load demand in the power system, okay. And this the level of water what you are seeing is nothing but the system frequency, okay. And the quantity of water inside this is nothing but it is representing the stored energy or the inertia, okay. So you can think of the scenario, maintaining an adequate level of inertia, that means the stored kinetic energy, right, will be helpful in case of say a contingency where you don't get any generation, okay. So let us say you stop this inflow of the water, but demand is still there, load is still there, right. If you have higher amount of water inside this vessel, then the reduction in the frequency will be less compared to if you have less volume of water inside this. So that is what is also happening in the grid. Following a contingency, if you have a good amount of inertia in the system, right. So what will happen following the contingency, the frequency nadir point, we use this point, this term called frequency nadir, the lower frequency what will reach, okay. If you have a good inertia, it will be on a higher side. If you have a lower inertia, it will be on the lower side, right. Through this figure also we can have further understanding of the importance of inertia. You can see, let us say the x-axis is time, the y-axis is the frequency. In India we have a 50 Hz frequency, right. So let us consider three scenarios. The red color is a system with higher inertia, followed by this blue color with medium inertia, followed by the green color which is nothing but representing a lower inertial system, okay. So as I mentioned, inertia means resistance to change. If you have a higher inertia, you expect a lower rate of change of frequency compared to a system having what, a lower inertia, right. So you can see that for the same system, if your inertia is going down, you are expecting a higher rock off, okay. Rock off is proportional to the size of your disturbance, okay, the contingency upon h, inertia constant. Higher is this value, lower will be the rock off. Then some of you may be thinking, let it be higher, what's the problem? Let this rock off be higher. What is the problem? let the frequency nadir point be a lower value. What is the problem? Right? I think some of you will have these questions. So the problems are related to some of the protection schemes actually, and also to the power system control aspect. We will try to understand that. After the disturbance, the inertia response that we get from the machines, it limits the rock off. As you see, more inertia, less rock off. Okay. So what is there in the system? There are some protection schemes which work on the principle of rate of change of frequency and low frequency. Okay, it is called low frequency demand reduction scheme, because see, traditionally if your frequency is going down, that means you have more load in the system than the generation, correct? So that means you have to knock out some loads. It's the at the last resort you want to do it, but it is there, you have to do it. So if your whatever the eligibility threshold is for that relay, it is quickly crossing those cutoffs, then your eligibility schemes are getting triggered and you are losing loads, right? So that means you can see for the same contingency here, the contingency remains same, contingency are not changing. Okay, let us say it's a loss of X megawatt of generation. That X megawatt of generation is the same contingency for these three cases, right? But you are saying that for the third case you are having more rock off and a lower frequency nadir. That means for the same contingency, this particular frequency response will trigger your LFDD relays, your rock off relays. Some embedded generations actually work on rock off. Okay, if rate of change of frequency is more, they will knock out themselves from the grid. So I will give you this example. You all of us are having friends, right? All of us are having friends. The organizer, Dr. Manoranjan, is actually my best friend. We are BTech classmates. So how will you define a good friend? Good friend means when you are in trouble, the friend will be there with you, isn't it? So let us say you have a contingency in the grid. Contingency means let us say you lost X megawatt from a conventional plant. And in your grid, let us say there are some embedded generations, some solar, some wind farms are there. And when you already lost a conventional X megawatt, do you want the other generators to continue to participate, continue to supply power to the grid, or you will want your distributed generations or the embedded plants to trip themselves? Of course, you want them to remain connected and support the grid, right? That's what I was referring to as good friend. A good friend is someone who will help you, who will be there with you, at least stand with you when you are in trouble, right? So that is what is the requirement. But if those plants experience higher rock off, higher rate of change of frequency, they may be thinking, oh, something is happening in the grid, let me first save my power electronic switches and converters. And if you are interested, these things have happened very recently in past. You can Google, there was a blackout in 2019 UK, August 9, 2019 UK blackout. The report is out, open access. You can access that report, you will understand what I am trying to convey. There are some things happening in the grid, some faults followed by some protection tripping, but unnecessarily some wind farms somewhere got tripped, okay, which was not expected. That those wind farms would not have tripped. Grid is in trouble, this would support the grid, right? Yes, this is what I was talking since last 3-4 minutes. Rock off and UFLS. Rock off, rate of change of frequency, and under frequency load setting schemes. Many operators around the world, they use this rock off and UFLS as a last resort, as special protection schemes to knock out loads or to knock out generations. Okay. So the maximum rock off limit to which the generating resources are required to comply and stay connected to the system differ between operators to operator. For example, you can see the left side table. The island operator, they use a rock off of 0.5 hertz per second for generator disconnection. The hydrocubic, they use 4 hertz per second for generator disconnection. The Europe, they use 2 hertz per second. Okay. Similarly, under frequency load setting, that means frequency is going down, you have more loads than generation, you are thinking to set some loads so that the frequency generation balance will be maintained. So PJM USA, they use 59.5 hertz. Of course, they work on stages. So there will be different stages for these thresholds. 59.5 is the first one. Whereas in Brazil, they use 57.8. Ireland use 48.85. So what I'm trying to convey is different operators use different ROC-off and UFLS thresholds, for their protection schemes. Okay. So for the same contingency, if you have less inertia, you may unnecessarily trigger some of these UFLS protection schemes, and then what will happen? You will lose loads, and that you can 19 blackout, if you go through the report, you will see that actually some of those loads were connected to the metro lines, and then passengers were stuck. This is what we need to avoid, isn't it? So that is where inertia comes into picture in a big way. The first thing is higher ROC-off system with lower inertia will experience higher ROC-off, and the another point is lower. So that needs to be considered for the future power system. I'll also of course suggest some of the things which can be done. So what I discussed, those are theoretical discussions. We also did do an academic exercise to see how the inverter based resource penetration is affecting the frequency response. So Gayatri, our PhD student here, did some works on that. So what essentially she did, she took different test systems, IEEE 9-bus system, 39-bus system in Northern Regional Power Grid, and the base case, we have all, let us say this is the 9-bus system, we have all the machines as the synchronous machines, conventional sources, and then she used to prepare different scenarios where one of the machines she used to replace with the type 4 wind turbine generator, and she used to increase the penetration level, say from 0% to 100%. And then for the same contingency, say in this case it is a bus 3 tripping contingency, the frequency response plot is plotted here. Okay. Here also it is quite evident that once we go for more and more IBRs, or essentially losing the system inertia, we can see that frequency at the point is going down and down, ROC-off also is increasing. Okay. The similar exercise can also be done for any other test systems. So now that we understood the importance of inertia, why is it important, right? Why is it important? Now that's why you will see that today and in the next maybe 10 years or so, today in countries where already IBRs have reached a substantial penetration level, those countries, for example UK, Australia, they want to do inertia estimation in near real time. They want to know as an operator where is the lower inertia region in my grid, then I should be able to do something, right? So inertia estimation in near real time is one of the most important research topic which is coming up, which will be there for next few years or so. As far as I know, there are few vendors which have come up with couple of techniques to estimate inertia sitting in the control room using the measurements. One is by the Dept technologies. I think National Grid UK did deploy their tool. The other technique is a machine learning based technique which is developed by GE, and it is also deployed in the control room of National Grid UK. So, but in general, there are 4 methods for these estimations. Inertia estimation based on status of all synchronous generators and synchronous condensers. If we have the status information, maybe through SCADA, then we can estimate the inertia roughly, or we can do inertia estimation based on the measurements. In our grid, a lot of measurements are coming, especially the measurements through the phasor measurement units, PMUs, syncophasors. So can we pick up some events and using the PMU data estimate the system inertia? I think this is also being tried in our Indian grid, Indian control room. And then measurement based continuous or intentional power stimulus, that's what I was referring to. Reactive technology has done it and they have deployed it in National Grid UK. and estimation of inertia using high speed measurements and machine learning. This is what I mentioned. G has tried to do so. Few things about our own system which you can get from our POSOCO report. This is the all India kinetic energy versus time. Okay, if you look at the time axis here and essentially the kinetic energy, or the you can also say that the amount of inertia we have in the grid with respect to time for a particular day. This was on 15th December 2021. You can see this pattern is more or less similar to a typical load profile we get, where we expect two peaks. One is the morning peak and the other one is the evening peak. So it can be observed that the overall kinetic energy trend is correlated to the daily demand curve. With the increase in demand, kinetic energy of the system increases with its peak aligning with two peaks, peak loading condition, as I said, morning peak and the evening peak. This trend can be attributed to more number of synchronous generators getting online with this demand. With the demand going up, perhaps during that time more synchronous machines are coming into the picture. Whereas even if this was the case for the all India scenario, if you look at the right side curve, interestingly, you are going to see a flat line. You can see the same thing. X axis is the time, y axis is the kinetic energy, but this is only for the northeast region. This is only for the northeast region. This is happening because in that region, perhaps the type of machines which are integrated to the system remain same throughout the day. Okay, that's what I mentioned. However, for some regions such as northeast grid, the trend of kinetic energy of the identified day, 15 December 2021, doesn't match fully with that of all India grid trend, right? Which can be attributed to this fact that almost same set of conventional plants in this region. I think northeast is having very nice hydro potency. So same set of conventional plants in this region remain connected for most of the day. So you are not seeing much of a variation. Why this is important? Why this is important? Why I am trying to show this? Because region wise inertia estimation is very important. Maybe I am sitting in the NLDC and looking at this figure, so I will be thinking this is true for the whole grid, but this is not the case. At the right side we are seeing a region in our own system where it is almost flat. So regional inertia distribution monitoring is one of the things which is going to be very important. And in the next few slides I will show, instead of even looking at the whole region inertia, we can also think of looking at the location of a particular bus or a substation. Okay, how far it is from the center of inertia of the system. So essentially bus wise inertia distribution is also going to be very important coming future, where we are not going to expect uniform inverter integration throughout the grid. Couple of more figures from the POSOCO report. We can see the trend of grid inertia from 2014 to 2021. Yes, you can see this is declining. Yes, not alarming at this stage. Perhaps the target that we have for 2030, maybe that time we'll experience the issues, but at this point of time it is still not alarming, but it is having a declining trend. And also it can be observed that even though inertia is on the higher side, the net inertia is reducing even with higher generation in the system, because this higher generation is essentially coming from the inverter based resources, which operate mostly in the conventional like MPP mode. The next figure is the all India demand versus inertia between 2014 to 2021. All India demand is going up, and the corresponding inertia also, if we do the curve fitting, also slightly declining trend we are seeing. As I said that instead of looking at the grid inertia as a whole, how about calculating something called inertia distribution? That means what we are looking at is how far each bus is from the center of inertia location of my grid. This is the work that we tried with Gayatri, So what we are saying that we come up with a logic called center of power based inertia distribution monitoring. So what do we do here? If we have PMUs streaming the frequency measurements, we can compute the FCOI, center of inertia frequency. If inertia H information is not available in the control room, then this is a weight factor. The active power coming out of the plant can be taken as the corresponding weight factor instead of the HI, the inertia constant. And then we compute the inertia distribution. So essentially, it is nothing but the area under this curve. So FBK is nothing but F frequency at a particular bus following a contingency frequency at a particular bus minus the frequency of the corresponding center of inertia. Okay. So what we are looking at, if I am sitting very close to the center of inertia, so I will be experiencing less frequency and angle deviation corresponding to a bus which is locating far away from the center of inertia. That's the logic, that's the physics behind this work. Once we compute this, we can do the normalization and find out the inertia distribution between 0 to 1. So all the buses will be their inertia distribution will be calculated between 0 to 1, and we try to apply this to northern regional power grid. It's I think 246 bus system having 60 generators, and in this case, so this is the signal line diagram of the system, very complicated system actually. What we did, we tried with the base case. So base case means all 60 machines are the conventional synchronous machine based system. Okay, so with the base case, we saw how the inertia distribution is. Okay, so using the previous slide, we calculated the inertia distribution for each and every bus, and then we grouped them into different areas. So group 1 to group 6. So group 1 means this green color is the area or the generators which are staying closer to the center of inertia. Okay, and group 6 is the machines which are away from the center of inertia. Okay, so this is the base case. So what we are expecting, if I replace now some of these generators with inverter based resources, I am expressing redistribution of this inertia buses, and redistribution of inertia distribution will lead to redistribution of these groupings. Okay, so this is the base case. For the base case, we got these groupings, and then what we did actually, we replaced some of the machines with the inverter based resources. Okay, and then we again found the grouping for the case 2. Again we had a case 3 where again few more generators actually of a particular group of the base case were replaced with inverter based resources. Essentially the logic is, you first find out the inertia distribution for the base case. Okay, and then let us say you start integrating inverters, either you replace few cases, few generators, or you add inverters, whatever it is, and then recalculate the distribution and see the grouping, how the groups are getting impacted. Okay, so we had 3 cases in these scenarios, and how to know whether the groupings are correct. As I said, the physics says that if a bus is actually closer to the COI following the contingency, it will experience less oscillation, deviation compared to a bus which is away from the COI. So in this case, if we look at we look at the frequency response for bus 19 and bus 36. So bus 36, if you look at, it belongs to group 1. Bus 36 is here, okay, green color, and bus 19, if you look at, it belongs to group 6. Essentially we took buses from 2 extreme groups. Okay, so because bus 36 is staying closer to the COI, you can see the following the contingency, the deviations are less compared to 19, which is away from the COI, and that's how we validate the groupings. And what we are trying to convey is, coming in the future control room, this type of groupings based on inertia distribution will immensely help the operator at least to know, okay, here is the group or region which is getting into the lower inertia zone, so I need to do something, okay, about it. Okay, this is about validation of the results. As I said, this philosophy can be deployed in the control room and for the near real time inertia distribution index calculation. So the framework goes like this. So we'll be getting the measurements from the PMUs into the control room, and we'll be deploying windows to do the IDA computation. And if there is some event happening in the system, for example, if you look at this graph, this is the real time IDA we calculated for the bus 159. So actually this bus is very much close to the center of inertia. So that's why the IDA value is very much close to 0. Remember, again I am repeating myself, the IDA is normalized between 0 to 1. If you are closer to 0 means actually you are closer to COI. If your values are near to 1, you are far away from this COI. So this particular bus was actually closer, and we did some contingency. The contingency was a reference power setting of the renewable generator at a nearby bus is increased at 180 seconds. So when it is increased, we can see the impact that this particular bus at 159 is observing impact on its inertia distribution. This can be actually very useful to the system operator in near real time scenario. Okay. We also tested that on a test bed that we have in the lab. What we did, see, we don't have the luxury of getting the actual PMU, right, PMU data. So what we do, we simulate the system. That Northern Regional Power Grid was simulated on simulation platform. We use DSC tools software. It's a software from PowerTech lab. We very rigorously use this for power system modeling, and they have one add-on called ePMU. It's a software PMU actually. So it can stream measurements using the C37.118 protocol. So the system is inside the PMU, and then we have a controller from ACL. It's called ARTAC, ACL 3350 ARTAC, which is outside of the simulation. But we can write our user defined code inside this controller. Okay, so that IDA computation that I saw few slides back, it was dumped here. This algorithm is here now, okay, inside the ARTAC. Once we compute IDI, that means then it has to be shown to the operator. So we have a remote monitoring software in some other lab where the PC is here. So essentially this ARTAC will then stream the IDI, computed IDI, again using the C37 protocol to another monitoring computer in front of which the operator is sitting. Okay. So this is how the workflow is. System is in GSC tool, IDI algorithm is in controller, the monitoring is happening somewhere else in the control room in the PC. Okay. So this test bed can be utilized at least for the academic studies, because we don't get PMUs, right, from the actual system. So this can be utilized to test various algorithms, not only this one, any algorithms you are deploying, you are developing using WAMS, this can be tested on this type of platform. Okay. So till now we discussed about the impact of inertia and how inertia monitoring is important, right? Before we close this session, we have to not this session, rather this part of this discussion. I mentioned there are two parts. One is inertia, the other part is protection, right? We'll take a break after inertia part. Before taking that break, we need to also understand how to address this issue, right? So we discussed about the issue. Issue will be related to rock-off, under frequency load setting, then how to take care of this issue, isn't it? So let us have a few discussion on this. The minimum inertia of the power system, how can we evaluate? You think of this. Now I need to evaluate, instead of how much maximum penetration of IVRs I can allow, just tweak the problem. What is the minimum inertia requirement? Okay. So just tweak the problem. So let us say the minimum inertia requirement we decide based on the maximum rock-off that my grid can survive. So now I essentially again from how much I bear to what is the minimum inertia requirement. From what is the minimum inertia requirement to I am going to what is the maximum rock of your grid can survive. So what the operators around the world are doing. The system operator in Ireland has introduced a maximum SNSP. What is this? Synchronous non-synchronous penetration level of 65% as of September 2021, with an ongoing review and an ultimate aim to increase it to 75%. It is mentioned that at least 20 to 30% of the power in the grid should be supplied by synchronous machines as far as Ireland is concerned. What about Australia? In the 100% Australian renewable scenario, AEMO, their operator, has considered a minimum of 15% synchronous generation in their market. Adequate distribution of inertia. Again, please mark this word, distribution of inertia. Adequate distribution of inertia. That is why I told you that I will come back to this particular graph. Adequate distribution of inertia. Okay, perhaps I will not be much worried here, where we have very nice conventional machines running. Perhaps I need to be worried more about this part and more about this part. Okay, that's it is not about how much is the total inertia. That's why I have been focusing on this word distribution of inertia. Okay, and the operators too. Okay, they have also identified adequate distribution of inertia across different regions and states in the grid to ensure that maximum rock-off limit is not breached anywhere in the system, irrespective of the size, location and loading. You can see now maximum in how much maximum penetration problem is now essentially boils down to how much is the maximum rock-off you can survive or withstand. Okay. What are the solutions? Let us discuss couple of possible solutions. Manage system inertia to prevent triggering of lock-off. So, can we manage system inertia to prevent lock-off based loss of pen triggering? Okay. So, essentially manage the largest loss in the system. In our system, let us say what is the worst case possibility, what is that megawatt which I can lose, and that should be my worst case. Is it 100 megawatt, is it 4000 megawatt? Prepare for that one. So, manage the largest loss in the system so that it will not result in a rock-off greater than the rock-off threshold, whatever our operator is using. So, that is one part. You decide what is the largest loss you can withstand, which will not result in the rock-off breach. Solution 2, otherwise bring one more synchronous generator in a region for additional system inertia, which will also deal with voltage and short circuit levels, because we are talking about inertia. The other aspect is grid strength, isn't it? Grid strength, short circuit levels, voltage waveforms need to be intact. Here we are looking at frequency dynamics, frequency response, isn't it? So, first calculate the largest loss of the system can withstand using the swing equation. Say to secure a loss of 1000 megawatt, this 1000 megawatt may be a 4000 megawatt for our grid. We need 200 GVS of inertia and rock-off limit of 0.125 hertz per second. Okay. So, this rock-off limit varies from operator to operator. So, essentially we need to look at the maximum inverter penetration from the perspective of maximum rock-off, okay, or the maximum essentially loss that I can withstand, which will not breach this rock-off threshold. Once we know our largest loss limit, that means let us I know that 1000 megawatt is the maximum loss. I cannot go beyond 1000. That means now we work out the number of units that need to have their output reduced to ensure that we are below this largest loss level. Okay. That means if I have fixed 1000 megawatt, I need to ensure that I cannot experience a contingency, general loss contingency of more than 1000 megawatt. So that means what we need to work out the number of units that need to have their output reduced to ensure that we are below the largest loss level. As inertia declines, the largest securable loss also declines. If we continue to decrease inertia, the largest secureable loss also declines. Okay. But the number of generators that are likely to generate above this value increases. That means as inertia decreases, we need to deload more units. Is it possible? Money aspect. We need to compare the cost of managing the largest loss. Okay. So if we assume that the price of increasing the inertia constant, a particular level of inertia, the most economic option shifts from managing largest loss to increasing inertia. Now it's a trade-off. Should I invest on increasing inertia? Should I invest on managing largest loss? So there will be a point beyond which you will realize that perhaps it is worth putting money into increasing inertia rather than managing largest loss. Okay, these two solutions that I discussed, this I took from again the National Grid UK blackout scenario and their possible solutions report. Okay, so these are not hypothetical; these are very much what they are thinking to do for their grid. Okay, so I mentioned that we will have the discussion in two parts. The first part was on inertia and the frequency response. This is the second part. Before I go to the second part, I would like to see if there are any questions. I'll stop sharing. You can unmute and ask questions if you have any. Or if you want to take 2 minutes break, that is also fine.
Participants can unmute your mic and ask directly.
Is there any questions till now, whatever we have discussed?
Participants, if you have any question, please raise your hands. No.
Okay, so it seems like there are no questions, so I'll move on. Let me share my slide again. Manojan, can you see this?
Yeah. Participants also, you can put your questions if you have any in the chat box. In the due course, expert will take care. Okay. If you are not able to ask directly.
Should we continue? Okay, maybe we can continue. You can hear me, right, Manojan?
Yeah, you please carry on.
Okay. So, in the second part, next half an hour or so, we are going to have discuss on the impact of this inverter-based resources on the protection aspect. Very, very important topic, and it is going to remain important for next perhaps 15-20 years or so. Why it is the case? Because see, traditionally when the power engineers they developed, they come up with the protection philosophies, right? Whether it is overcurrent protection, let us say to start with overcurrent protection. So what we expect intuitively, if there is a fault, there is a short circuit, then we are expecting a higher amount of current, isn't it? The source will provide a higher amount of current. So if my line or circuit or the equipment under consideration is having an overcurrent relay, it will detect a fault because the current flowing through the device is more than the pickup value, isn't it? So essentially a higher amount of current following a fault, a short circuit, is intuitively expected, right? Similarly, if there is any unbalanced fault happening in the system, we expect that along with the positive sequence quantities, there will be negative and zero sequence quantities. These are the by default expectations. But is this correct for an inverter-based resources? That is what we need to look into and retrospect and do the brainstorming. So, motivation, increasing penetration of IBRs unpredictable short circuit behavior, because those who work in the domain of power electronics converters, they will be appreciating, they will be knowing more that they put a current limiter, okay, in the control circuit, because they want to safeguard the switches of the converters. So, you know, the inverter based resources are not expected to provide, you know, a fault current of beyond 1.1 to 1.2 per unit following a short circuit, okay, which in the conventional case we used to see for the synchronous machine based resources, you know, fault current as high as 5 per unit, 10 per unit going up during the fault scenarios. So, if that is what we are referring to, unpredictable short circuit behavior, that is not only the issue with the amount of fault current expected from the inverter, not expected I should say, which you can get from the inverter. At the same time, the control of the negative sequence currents during the unbalanced scenarios, how the negative sequence response will be from the inverters, right. And typically, you know, the protection engineers, they use the short circuit programs, and they assume that the system is conventional, and the sources can be assumed as voltage sources. But as far as IVRs are concerned, traditionally, I am talking about traditionally, because yes, now people, standards are coming up and people are trying to you know, enable the inverters with more sophisticated controls, but traditionally it is a voltage dependent current source, right. And this type of unpredictable behavior from inverters, current limiting devices, voltage dependent current source, the dynamically changing phase angles because of the control action. So, and the protection actually is designed assuming that the source is a voltage source, very nice voltage source. So, then that means what I am trying to convey is all these legacy protection schemes need to be revisited, and their performance need to be evaluated in the presence of inverters with different control philosophies. That is what also we are trying to do with few students. Sarthak works on the directional relaying perspective, and some other students are also working on this particular very important problem statement, okay. So, one or two examples figures I will show to you, so that you will appreciate the issue, because the first thing is always to appreciate the problem. Yes, actually this is a problem, then we think about the solutions, isn't it. So, what he did actually, he took he built this Segre 14 bus system and connected a 4 megawatt IBR to this particular bus 6, okay. And the relays under consideration are R65 and R56. So, if you look at the R56, if there is a fault happening on this line, R56 is actually seeing the response from the conventional grid. So, the response that the R56 relay will see to this fault is actually being fed by the conventional resources, whereas whatever R65 will see is actually the response of the inverter, okay. So, quite as I was telling in words, I think this is something which you can see visually. Fault current for that particular fault current seen by the relay R56 I mentioned, it is actually seeing what the conventional grid is feeding. So, this is the signature we expect, right. This is the signature we expect, very high fault current, a decaying DC component. This is what we expect for the conventional system, right. Whereas the R65, the relay sitting here, which is only seeing the response coming from the inverter is actually feeding this through R65, you know, hardly any changes, actually, hardly any changes. So, if you are using an overcurrent relay and you have used some pickup value, okay, the pickup value is 2000 amps, if it is more than that you trip, well, then from the other side you are completely blind, okay. Because why it is happening, the inverter, it is fault current is limited to 1.1 to 1.5 per unit theoretically, and then you don't expect such high fault currents, right? So that is what is one of the challenges, and the other challenges is, as I said, if you are doing unbalanced fault scenarios and you are using relays which work on the negative sequence components or the zero sequence components, okay. So in that case, also you may see the relays are unable to reliably detect the faults. For example, in this case, what he did, he used relays which use the negative sequence current philosophies, okay. You can see this red color paint is the negative sequence current seen by the R56, that means because this is what is being fed by the grid, whereas the blue color is almost flat, right, fed by the inverter. So naturally, if the relay 56 is not seeing any unbalance, then there is no trip signal coming from the 5-6 side, from the inverter side. So this is also one of the problem that you can see, that legacy protection schemes need to be revisited. Now it's a fight actually. I always use this term in my class. So the inverter owner will say, see, this is your problem, protection people, you do something with your relay so that it will adapt to our response. The protection engineers, the relay manufacturers will say that no, why should I change my philosophy? You do, during fault you provide me response which should be very much similar to the response of a synchronous machine, right? So so that this discussion will always continue. Perhaps the grid codes are going in a way where now the inverters owners actually are supposed to take care of these issues and not the protection engineers perhaps, but of course we can come up with logics in the protection itself so that it will not be dependent on the source which is feeding the fault. So that's called, some people use this term, control agnostic relaying philosophy, where it doesn't matter whether your inverter is working on MPPT or LVRT or HVRT, whatever it is, your relay is intelligent enough to detect the fault. So once we saw couple of problems, and I mentioned that now different standards are coming up, okay, whether it is North American standard, it is German grid codes, in India we have the grid codes from the CEA. What is that it is asking the inverter owners or the plants to do? Two very important things that they are supposed to do is low voltage ride through, okay. What does it mean? I'll go back to my previous example. If you are a good friend, you will stand with your friend during his or her bad times. That is what is the meaning of NVRT, low voltage ride through, okay. So you have a inverter, okay, you have the polling station, this is the substation, ISTS substation, this is the point of interconnection, this is where the compliance will be checked, and this side will be your grid, okay. If there is any faults happening in the grid, okay, low voltage scenario is being created, you should not isolate yourself randomly, okay. CA has come up with this type of curve. This is the time axis, this is the voltage, okay, Vt upon Vn terminal upon the nominal voltage. If you are in this region, okay, let us say this is the 0.85 per unit, this is the 0.15 per unit, okay. If the voltage is in this region for this much of time, you should remain connected to the grid, okay, and if it is beyond that, you can disconnect yourself. That is what is LVRT. The name is low voltage ride through. So the converter based generation stations connected to the grid shall remain connected to the grid when voltage at the interconnection point POI, okay. I will encourage all of you to please go through IEEE 2800 standard, because many a times I have seen people get confused with POI, POC, PON. No, this should not happen. So we should be very clear about the abbreviations, where is the compliance, where the compliance need to be checked, okay. So at the point of interconnection, okay, on any or all phases, all phase dips up to the level depicted by the lines of this particular graph. So it is, you will remain connected, but what will you do? Okay, as an inverter, what will you do? First, because this is a low voltage scenario, you should provide voltage support. So that means you have to supply VAR. So the VAR support is given the priority during the LVRT. What should be the response time? It should be done within 30 to 40 milliseconds. You supply the VAR, so that is something called a K factor, which you can get some understanding if you refer to the 2800. Using the K factor, we decide how much should be the VAR. Once you decide the VAR requirement, if your inverter still has some capacity, you can give the corresponding remaining component to the active power. Okay, but first needs to be the reactive power should be given priority, right? Then once the fault is cleared, is very important. Once the fault is cleared, then what is mandated? At least 90% of the pre-fault level the inverter should reach within 1 second of the restoration of voltage. This is also very, very important, and this is where I will discuss few cases. You will see many inverters are struggling. So wherever you are giving X megawatt, then you suddenly reduced your megawatt, increased your MVR to support the grid during fault, right? Once the fault is cleared, again you should at least reach 90% of the pre-fault level power, whatever you are giving X. So 90% of X megawatt within 1 second. That is what is very, very important, and that is what is not happening in many cases actually. So this is about LVRT. Similarly, HVRT, high voltage drive through. If high voltage, naturally we understand we don't need to provide VAR, rather we need to absorb VAR, right? So the generating station connected to the grid shall remain connected to the grid when the voltage at the interconnection point on any or all phases rise above the specified value, which is given in this curve. You can see this red color HVRT, and the values are given. So the voltage is more than 1.3 per unit. No need to remain with your friend. It is a very dangerous situation for you also. So you will trip instantaneously. Voltage is between 1.2 to 1.3. Time limit is 0.2 seconds. 1.1 to 1.2, 2 seconds. Voltage less than 1.1 continuously you have to be there. So this is what is referred to as HVRT requirement. I am setting the standard first before discussing the use cases. We should understand LVRT, I need to provide VAR support. VAR support is given the priority, megawatt should go down. HVRT, I am supposed to absorb VAR. Of course, there are limits given beyond which I should trip. Okay. Once the standard is fixed, we should understand that it is followed. So I'll be analyzing, give you one use case of 13th May 2023, one grid event near the Rajasthan area, the renewable energy complex. So event description, please look at this diagram. It was a fault case actually on this particular line at 11:51, 765 Bhadla Bikaner circuit 1 tripped on a face-to-face fault. The bus voltage dipped to 0.65, which is the LVRT threshold, below LVRT threshold because of this fault. Okay, and we'll see, I'll show you few diagrams, you will see that surprisingly, after the fault clearance, the voltage shoots to 1.1 per unit. And during this event, this is a very natural event. It's not a very strange event, right? A fault happens, it will happen. Protections are there to trip, isn't it? But because of this, so many other events happened, which was surprising. And if you go back to 2019 UK blackout also, those are also the similar events. Fault happened, lightning strike, fault happened, fault cleared. Very conventional scenarios as far as power engineers are concerned, very day-to-day activity. But unnecessarily somewhere some wind farms tripped, that is what was very surprising. Similarly here also close to 7,000 megawatt of generation loss on over voltage. Frequency drop, if you lose this much of generation, frequency lost to as low as 49.4, which has actually triggered our under frequency load setting scheme. and because of the under frequency load shedding, close to 4,000 megawatt of load were lost. You can see very conventional event, but close to 7,000 of generation loss, close to 4,000 of load loss. So what happened actually? Let us try to dig into this. If you look at this figure very carefully, left side, we'll try to understand this figure carefully. This is time, this is y-axis, red color is megawatt values. This blue color is the voltage in per unit. Okay. So if you look at the once there is a fault happened, you can see the red color megawatt from the renewable energy plant, close to 300 or something. Fault happened, so naturally megawatt should go down as expected. So good, they did very nicely. But the next point was you should able to recover 90% of your pre-fault generation within 1 second. This is the 1 second time instant. You could see very sluggish response. Plant has failed to recover to 90% of the active power within 1 second. This is not what was desired. First thing. Next, this plant. So this is plant FTHL. This is some other plant FDLF. You see, again red color. Megawatt was good. Fault happened. Event happened. Megawatt goes down, but it could never recover. No recovery to 90% of pre-fault active power. It could never recover. Third, this one. This is the MVAR, reactive power. Okay. So green color was the reactive power, right? So you can see that event happened, it momentarily goes down. Okay, and then this particular plant FTHL has increased the reactive power absorption during the low voltage, while it has increased the reactive power injection during high voltage condition. Very difficult scenario. You see already this blue color, already this is more than 1 per unit, right? It's more than 1 per unit. When it is more than 1, that means you have a high voltage scenario, right? You are supposed to absorb VAR, not inject VAR, correct? So there also you could see this plant is not strictly following the grid code, whatever is mandated. Let us go through it. We could see all these three graphs. The behavior of this RE plant was opposite to the grid requirement, what we have mandated. Plant has either recovered to their pre-fault active power with a delay. Okay, this plant, it has recovered but with a very substantial delay, or have not recovered. This plant, it could never recover. Then plant FTHL has not recovered to 90% of the pre-fault active power within stipulated 1 second, this scenario. This FDLF has not at all recovered. Further, in LVRT condition, plants shall maintain the reactive power priority, and therefore shall increase its reactive injection during low voltage condition. This has not been complied by many plants. As shown in the figure, this particular FTHL plant has behaved in opposite direction. It has behaved actually in the opposite direction. When you are in LVRT, your MVAR should go up. When you see voltage is going up, you should absorb reactive VAR rather than injecting. If you operate in the opposite way, actually you are not helping the grid, and that is how these things happened. Okay, so very interesting scenario. Few more slides. In many cases, plant has either reduced their active power sensing the HVRT conditions, or have not responded to the HVRT condition as mandated by our grid code. As shown in this particular figure, BDLO, this particular plant has remained connected even when voltage at the POI remained above 1.1 per unit for more than 2 seconds. Here the point of interconnection voltage. You can see this is the 1.1, so it is more than 1.1, and as far as our the table is concerned, this one, okay, it should remain 2 seconds, 1.1 to 1.2, the limit is 2 seconds, right? So even if it is above 1.1 for more than 2 seconds, it is still there. On the reactive power side, many plants have behaved opposite to the grid core requirement by contributing more reactive power injection during high voltage. It is like a crime, isn't it? This 1.1, you can see this blue color is more than 1.1, and this particular plant is actually injecting reactive power, isn't it? So essentially, I do not know, maybe some issue with the controller, it is actually acting in an opposite way as what was expected. So with all these use cases that we discussed, now let us do some brainstorming, and all these questions are very hot topics, research topics these days. Why there is rise in voltage immediately after the fault clearance? Why there is dip in the voltage after 5 seconds of the fault? Why there is loss of renewable generation during the faults? We saw some generation, tripped. So already we have discussed, I'll just go through it quickly. Essentially, for the first question, this is the answer. Either the reactive power support is no, there is no reactive power support, or opposite reactive power support, or delayed reactive power support plus delayed clearance, delayed active power recovery is actually what is contributing to the over voltage. Once there is over voltage, what happened? Many transmission lines also tripped actually for that particular event. In case of high voltage after fault clearance, as explained above, some IBRs are entering into the HVRT mode. These IBRs shall support the grid with reactive power absorption. Remember absorption, because you are in the HVRT. However, in the absence of any such support, there is gradual rise in the voltage, leading to more IBRs entering through the HVRT mode, thereby resulting in the further rise in the voltage. Loss of RE generation during fault, loss of evacuation path, because high voltage many transmission lines also tripped, so you lost the evacuation path. Incorrect LVRT and HVRT settings or the responses that we are getting from the plants, that is where caused the trippings. So with these discussions related to protection, what we did, what are the key takeaways from this? We need to standardize the IBR response. Standardize the IBR response. That means all the inverters, all the farms, inverter generating stations should comply to the grid code very strictly. Okay, because see, I will be able to set my protection correctly if I know that definitely the response from inverter will be like this during fault. That is how protection was operating very nicely, very reliably since last 100 years or so, because we know that this is how the voltage source will respond to a fault. But now I need to standardize the IBR response during fault. Definitely this is the signature I am expecting, then I can design the protective algorithm. Controlled inverter response generally does not start to occur earlier than one cycle from fault inception. We can see, we just saw that, see, you are connecting the inverter, okay, fine, you have the measurement of the terminal voltage based on which you are deciding your ID ref and IQ ref, okay. So if there is some issue, you are sensing the voltage, you are changing your ID ref and IQ ref to support the grid, absolutely fine. But what is the response time? How quickly you are changing your reference, and how quickly your actual quantity is following or tracking the reference quantity. Because remember, traditionally the transmission system protections, they operate the relays within one cycle, they should detect. They detect within 1 cycles, and the breaker operating time may be 3 to 4 cycles. So within the 5 cycles, game over, right? Within the 5 seconds, game over. But now, am I going to take a decision? Am I going to take a decision that means that within 5 cycles, when my inverter itself is not stable, my inverter itself is trying to track the reference, or the reference itself is trying to change the value based on the POI measurement, right? So that is where you can refer to this document, this very interesting document, the workshop on that is North American Electric Reliability Corporation. There are many vendors, protection vendors, inverter manufacturers, OEMs. Many people came and they did a discussion about this aspect. Okay, so one of the aspect was inverters response generally do not start occur earlier than one cycle, but from the protection perspective, we usually detect within one cycle. So there is a dilemma, right? As synchronous generations retire, there may be opportunities to slow down the protection system operation. See, why we used to clear so quickly? It is related to what? Transient stability, right? Critical clearing time. So now that we are replacing the synchronous machines, there is a question mark. That is a very interesting question. Can I slow down the protection? Do I really need to clear the fault within 5 cycles? Question mark. I am not saying yes we should do, no we should not do, question mark, which is again coming from this workshop. The concept of CCT may be revisited. We did a work with Gayatri. We revisited the concept of CCT and we saw the possibilities where we can move as we go on integrating more and more inverters. And the last point is very, very, very important. Continuous research and EMT simulations. Yes, for large scale studies, we are very familiar with phasor simulations, RMS simulators such as PSSC and PSLF and DSA tools, so on and so forth. But with all these inverters getting integrated, almost all the operators are now saying no, we should go for EMT. And then there is a trade-off. Can I model the whole grid with EMT? And that's where the core simulation comes into the picture. Core simulation where you model the inverter, its control part in the EMT, the rest of the grid can be modeled in RMS simulator. So it's called hybrid simulation. Okay, that can also be attempted, but continued research and EMTs are definitely required. Okay, so some of these problems that we discussed in this session actually are very relevant research problems. Sub-cycle over voltage I mentioned. Many grids, many operators are seeing these issues. Why this is happening? Who is contributing? Oscillations. I did not touch upon oscillations because I know it will be overwhelming with so many things getting discussed. Oscillations, type of oscillations, the interactions of inverters with the conventional modes. So forced oscillations. So all these things need to be revisited. Okay. So EMT simulations are needed in this area to continue to explore the optimal injection and prioritization of the currents from the IBRs, and to better understand the possible inverter level interaction or the transient conditions, how the dynamic response of the inverter control system is actually affecting the grid dynamics and monitoring and protection. Okay. Few closing remarks. The inertia and kinetic energy trends we are seeing a declining trend, right? So inertia monitoring, inertia distribution monitoring is very important. Okay. And we need to revisit the thresholds or the settings of the LFBD and Rockoff relays. Okay, we need to understand the impact of this IBR controls on the short circuit programs, the protection philosophies, all the legacy protection philosophies, distance, overcurrent, etc., etc. Okay. So before I close, few things about our group, how and what we are contributing. So some of the activities that we are doing at IIT Palakkad in our lab, I am putting those activities on my YouTube channel. It includes some modeling using PSCAD, some software development activities. This you can see the test bed that I showed we used to test our inertia distribution algorithm. If you are interested, you can see them, and materials, if you are interested, you need to email. So one of the software we developed very recently, I will demonstrate that. That is used for oscillation monitoring. Let me go back to Manrajan. Can you confirm if you are seeing the BigSync page?
Yes, it's visible.
Okay. So this is apart from what I discussed, we also work on this software development activities for data analytics, grid monitoring, post event analysis kind of application. This I will demonstrate. This is one software which is developed here at IIT Palakkad by the students, and this application can do what offline engineering analysis. Okay, so what I'll do now, I'll be using this software to analyze oscillation, in one of the ISO New England test system. So you can see there are few modules which are being integrated, analyze and detect. So I'll be importing a data, and the operator can import the data and see whether there is an event happening in the system. If there is an event, what type of event? Once I know what type of event, where it is coming from, and its characterization. Okay, so first let us analyze and detect. So I'll go to what? I'll go to analyze and detect, choose file. As I said, ISO New England, one of the test cases I'll take. ISO New England is one of the operators from US. So I'll check their data. You can see at the left there are different substations. Let us say you click any substation, there are different lines connected to a substation. For example, substation 2 is having 3 lines, line 2, line 3 and line 4. Let us say you click, at the right you can see different properties. So from these substations you are getting frequency measurement, voltage magnitude, voltage angle, current magnitude and current angle. You can plot. So you can see I have plotted the frequency measurement. Okay, so I want to know is whether there is an event happening in that particular system using the data. So once you plot it, you click on detect event. Okay, event detected. So algorithm, whatever we have incorporated, it is detecting the event. Now I want to know which type of event it is. So user can set some thresholds, then classify event. You can see impulse event false, generation loss event false, load loss false, oscillation event true. So that means in that data there is an oscillation event. So you can click here, you can further do some analytics. So this is oscillation, but from where it is coming? If I want to know from where it is coming, so I need to go to this model OSLP, oscillation source location program. Click there, again choose the file, same file I will choose. I know that there is oscillation, but from where it is coming. Okay, so here you can again select any data you can actually select, and then you have to select a window because it's a large signal. You select a window. See, intuitively you can see there is oscillation here, right? So let us say I will select a window from here to here. Okay, and then you click on locate the source. So you can see whatever algorithm we have deployed, it is saying this one. So it is doing some ranking. Substation 2 line 4, there is an oscillation. Substation 2 line 4, there is an oscillation which is having a highest DEF. Now I know that there is an oscillation. It is coming from substation 2 and line 4. Now I want to further diagnose that oscillation. What is the frequency of oscillation? What is the damping? So for that I need to go to this oscillation characteristics. So again you go to that, import the test case. So what the previous program said, that there is an oscillation coming from substation to line 4, right? You add, then click extract modes. So we have developed some algorithms which are integrated, which will extract the modes from the signal, and then it will show, okay, you have these modes and the corresponding frequency of oscillation, amplitude and damping. You can see 3 modes it is showing, but the first 2 are having good damping, 28% and 13%. Any power system operator will know that these are good damping actually. This particular mode 1.16 Hertz with 1.14 damping is a dangerous mode because the damping is less than 5%. Okay, and energy contribution is also more. So this mode 1, so I need to dig into this mode 3, right? So user can select mode 3 amplitude. You can see the mode 3 amplitude that means this mode 3 got excited because of some event in their system, and you can see their amplitude. Okay, yeah. So this is, I just wanted to show some software development activity Before I close, let me. Manojan, you are seeing my slide?
Now slide is not visible.
Okay, let me share again. Now it is visible?
Yes, yes.
Okay. Okay, so closing remarks, what and how we are contributing this. Yes, this presentation will not be complete if I don't acknowledge my students. The inertia work I showed is from Gayatri, and the oscillation work was from Arup. The software was developed entirely by Rishabh. Of course, I gave the algorithm, but the development work was done by Rishabh. Protection work, what I showed, he was the MTech student, now he is with GE, was by Sarthak, and some other students also contributed. Yeah, so yeah, I am done. So we can take some questions if we have some time with us. Maybe I
Yeah,
will come.
participants. Yeah,
You put in
participants.
this
You
chat
can.
box. I am having water and come back in 1 minute. Huh?
Yeah,
I will
sure.
get some water now. Huh?
Yeah,
You can get question on the chat box if they want.
yeah, sure. Participants, you can put your queries in the chat box. Expert will address all these.
Hello everyone. Participants, we are requesting if you have any question, please raise your hands or put in the chat box. I think देखो था क्या? Hello sir. Participants, if you have no question, please turn on your camera so that we can take a group photo.
Please put your questions, whatever you want to ask to the expert, please in the chat box. He'll address. He has gone for a sip of water. He'll come. Please put your questions on the chat box. He'll address. Expert will address everything.
Yes, I am back. So, is
I
there the
think you
question?
can check. I think some two people. Yeah, I think
Where to check?
you can check the query
Or QA.
in the chat. In the chat, you can check.
What is the maximum limit for array penetration in a grid? Okay, as I said, this is one of the questions that operators have been asking. There are different criteria we need to follow first of all. Okay, one of the criteria is, can we look at the maximum rock of the grid can withstand? I mentioned that one of the possibilities. Let us say we decide 1 hertz per second is the threshold. Okay, we have set this protection setting at 1 hertz per second, for example. Okay, so we need to see for a particular scenario of inverter based resource integration and the worst case contingency. Okay, worst case contingency, my rock off should not breach 1 hertz per second. Okay, if it breaches, that means I have to reduce the penetration, or I have to increase the inertia. But mind you, this is not the only criteria we should be using. We should also be thinking from the small signal stability perspective, which we did not touch upon. Okay, what we are talking from the frequency response perspective. Frequency response perspective, maybe we can go ahead with a rock off, okay, as one of the criteria. We can also look into the same problem from the small signal stability perspective. Okay, and some people may also say that I need to touch upon this problem from the transient stability perspective. So there is not a single answer to this question, but as I gave you a few examples, the Australian grid, they have said that some maybe I can go back to the slide. Sharing the screen, or I'm not sharing the screen?
Yeah, yours. I think your screen is not shared now.
Okay, let me just do that.
Yeah.
Let me share again. Am I sharing now? Yes. So you can see that Austrian grid, they have decided that a minimum of 15% synchronous generations should be there. Okay, and as far as the Ireland grid is concerned, their target in 2021 was 65%. Okay, and they have come up with a quantity called SNSP, system non-synchronous penetration. Okay, so with 65% also they have the ongoing review, and their ultimate aim, what is their ultimate aim, is to increase the limit to 75% and beyond. But it is mentioned that at least 20 to 30% of the power in the grid should be supplied by synchronous generators value. So essentially they both of them are in this on the same page, right? So perhaps once we reach 50%, then we should see how to go about it. Yeah, rock off is one of the criteria. I hope I could address this. But that is the only one question I could see. Is there any other question?
I think yeah, you can see the
There
one
is
chat box also.
Sir, kindly explain the concept of LBRT and how it may impact RES generation. LBRT, okay, I'll go back to the slide again. Share. Yes. Manoj, can you see the slide deck?
Yes.
Okay. Let me go back to the grid code. Yes. Okay. So let me pull the pointer. So LBRT. So LBRT means low voltage ride through. Okay. So you look at this particular figure. Okay. Let us say these are your inverter plants, solar or wind. This is your pooling station. Okay. This is your point of interconnection. Okay. This is your point of interconnection. That means, and then there will be some lines here. So let us say in those lines you have a fault. So earlier what used to happen, even now what is happening, many of the conventional plants, the moment some disturbance happen, they see some rock off, they will trip. which is not desired. You go back to my earlier example of a friend. There is some issue, you should not trip. You should help your friend. Grid is your friend. How will you help? If there is a fault, low voltage happened. Low voltage happened means what? See, traditionally these plants, this inverter-based resources, solar, traditional how you operate using MPPT. You say that okay, whatever maximum power I am generating now, I should dump it to the grid. But during fault, you should not do this. Fault means you have a low voltage scenario, right? You should provide VAR support to the grid. So once you are under LVRT, that means you are essentially supporting the grid by providing VARs. That should be the priority. Now you have two components. One is active component, one is reactive component. Reactive component you are giving first priority. Reactive component your first priority. Then if you have still some bandwidth as far as your inverter capacity is concerned, if you have still some capacity available, you can give the active power also, no problem. Okay, but you should remain connected. So that is how this figure is telling. X axis, this is y axis. Okay, this is Vt upon Vn. Okay, Vt is actual voltage upon nominal voltage. Okay, if let us say you are between this is 0.85, let us say this is 0.85, this is 0.15. Okay, if you are in this region, okay, let us say the voltage is say 0.7. So voltage became 0.7 should not mean that you will isolate yourself. No, no, no. If it is 0.7, you can see till this much of time you can remain connected. This is the time is in millisecond. Okay, so that is what we are referring to as LVRT. And that response time also, as I said, you should remain connected and provide VAR. But again, what is the response time? You should provide that support within 30 to 40 milliseconds. I hope that is clear now. That kindly explain and how it may impact the RES generation. That is how it is also impacting, not essentially. See, I am looking from the grid perspective. Okay, so RES generation means you are earlier giving in the conventional before the fault, you are giving only megawatt to me, for example. Okay, you are operating at unit power factor. Now using during LVRT period, you are helping me with the what reactive power support. That means internally you are changing your ID ref and IQ ref, so that you have the fixed capacity. Inverter capacity is fixed, right? Earlier you are using the full capacity for megawatt. Now you compromise. You give priority to MVR and the remaining should go to megawatt, like this. That is how it is impacting the generation. I hope it is clear. Mimansu. Any other questions?
Participants, you can also turn on your mic and directly ask if you wish. Okay, if you don't have any questions, it's a nice and wonderful session, Manas. It was really great. After the lunch session, you took so much. I think the energy, it requires a lot of energy to prepare this kind of talk. It's very nice and very, I think, very basic. If someone who really wants to work on real renewable energy system, it will greatly help them. Also, the software you have developed by your group, it is very nice. People can take help of that software. As Manas referred, they can follow their YouTube channel and see how they can really develop from the scratch, and then can simulate it and see what is really happening. It is nice to see, Manas, really. Thank you for accepting our invitation and with your busy schedule and making it out. Though I know it's an online session, it is not that much interactive for you the way you want. But hope I'll make it out soon at NIT Rourkela for you. Thank
Yes,
you.
yes.
I request all the participants to please turn on your camera so that we can take photos of all.
Yeah, next time you plan for offline. Offline is having.
I understand. I know the energy you are keeping, it needs a really offline, because online people are not that much interactive, I'm feeling. I hope next time I'll keep online.
Sir, is it open source software? Are you talking about BigSync or are you referring to the software models? Software models, YouTube video you can follow to develop your model. If you want model, you can write to me. I will share with you along with the materials. The BigSync software, yes, everything is developed using open access platform, Python. If you want to explore, you write to us, we will be able to help you. You can use it. Actually, we did not use anything which require license. The languages, all things are open access actually. BigSync, yes, it is open access, yes.
Please turn on camera. I have given the access. All of you, please.
One more new chat. Okay.
Thank you. Thank you. We have taken. Thank you all for your patience after the lunch. Yeah.
Thank you all. Thank you, participant. Thank you, Manoranjan. So I can leave now.
Yeah, yeah, sure. I'll be in touch with you. Sure.
Okay. Take care.
Mm,
Bye
bye
all.
bye.